This is two sections that we're going to do, part one and part two, on exponentials. And you will notice here that I have put the x of the exponent word up as a superscript, looking like an exponent, because that's what exponentials are. They have x in the exponent. So this is applied more directly to solving equations with logarithms and exponentials. So the first exponentials that we want to illustrate is just the bare formula that there is a with a base to the x exponent or a t exponent. The a can be positive or negative, which means it can flip over the x-axis, either up or down. B is the base. X is an unknown variable. Here is the wider usage of it is a b to the x minus h plus k. And we've referred before to a, h, and k in transformational graphing of our parent functions. Well, h is a horizontal shift, left or right, and k is a vertical shift, up and down, of the parent function. The horizontal asymptote is y equals k. Typically, that's y equals 0. That's kind of the default. So when we see a graph, we'll notice either the horizontal asymptote is either here at 0, or wherever k goes, it would shift up or down with that. So the first exponential that we want to do is y equals 2 to the x power. This is called a base 2. This is also called a doubling formula. And so if we plug a negative 3 in for x, you'll notice that as x gets larger, y gets larger. So that's an exponential growth. As I plug in negative 3, I get 1/8, and that graph's right here. I plug in a negative 2, I get 1/4. That graph's just slightly higher than that. Negative 1 is plugged in, I get it 1/2, again, slightly higher than that. Then I plug in 0, anything to the 0 power is 1, and then a 1, and that gives me a 2.12, and then 2 squared is 4, which gives me the last point, and so this graph goes up, and grows rapidly, and y equals 0 and y equals k are horizontal asymptotes, are the horizontal asymptote, and so that's an illustration of 2 to the x power. Here's a graphic to show population growth. You'll notice that it starts back really early in time with 1 AD at 150 million, and then it jumps up to projecting the year 2020 when we have 8 billion people in the world. So this is an exponential growth. The pattern is population growth over time equals the initial amount. We could either say that's in 1350 or back at 1 AD. E, which is our 2.71828, to the k t power. The k is to be determined by the pattern of the growth. So to graph those points on a chart, now I'm going to use 1700.6 billion, 600 million, up to 8 billion in 2020, and I've marked those off kind of closely: 1700, 1800, 1900, 1950, 1985, and so on. And put the points on the graph, and you can kind of get a graphic of what that looks like. The rules of exponents were rules that were used early in algebra. They are the zero exponent rule, the zero power rule, the negative exponent rule, where you drop the numerator into the denominator and make the exponent positive, or vice versa. Then the product rule is adding exponents of like bases. The quotient rule is subtracting exponents of like bases. And the power on power is multiplying powers on powers. An example of that could come up would be 4 to the m. Let's go over here. Let's pull down our formula first. Let's try 3m times 3 to n. Notice the like bases, so we add the exponents. Let's reverse that process a little bit. What if you had 2 to the x plus 2? Well, reversing this process up here, that would mean this is really 2 to the x times 2 to the second. Now, we're not used to doing this. That's just the reverse of this rule. It's okay to do the rule from left to right, but it's also okay to do the rule from right to left. Something you may not have thought about. Next, we go on to the remainder here, 4 to the m over 4 to the second. Again, we subtract the exponents. Again, not something that is unusual, but let's reverse that. What if I started out with 3 to the m minus 2 power, and I wanted to reverse the rule and go back to 3 to the m over 3 to the second? This is sometimes used to prove equivalent statements. And the last one here, a good use of this would be 243 can be written as 3 to the fourth. Because the bases are equal, the exponents must be equal. So here's an illustration of the rules of the exponents. Exponential decay would be when you had a negative exponent or a 1/2 base, a base that is less than 1. And so in this case, when we plug that in, we get 8, which was the opposite when it was base 2. And then we plug in a 4. We'll see our 8's way up here. We'll plug in a 4, and then we'll plug in a -1, and that reverses the fraction, turns it over into 2 to the positive 1. So we get the point -1, 2. And then we plug in a 0, which is 1. That's an easy one. We plug in a 1, which is 1/2, and then we plug in a 2, which is 1/2 squared, 1/4. Again, you can see that in this case, as x gets larger, y gets smaller. So that's why this is called a decay. There's the horizontal asymptote still at y equals 0. So here's a half-life illustration. This may or may not be a good one, but at least it shows how to use the half power, the half-life. In this case, we can see that the half-life was 25 years. And so to set up the equation, we have time over 25 years. That gives how many times the half-life occurs. Notice the initial mass is when time equals 0. So the initial mass would be 10 grams, and of course that's the initial number out here in front. And then as we apply that, let's go to 80 years. That means the half-life would occur 3.3 times, which is illustrated a half times a half times a half. That's 3. And this would be 1/2 actually to the 0.3 here, not 0.2. Mess that up. And that would give me 1.088 grams. So I started out at 10 grams. 80 years later, it has decomposed to 1.088 grams. And the last thing we'll talk about is E. E is the number 2.71828. This is the natural base that's observed in nature. We saw it in population growth. We also see it in radioactive decay. We also see it in the growth of animal populations. The actual formula is here. And if you track this, this is where e to the x and natural log base e come from on your calculator. E is named after a guy named Euler, Euler, from Basel, Switzerland. He's called the greatest mathematician of all times. And of course, he has a button on the calculator dedicated to him. So here's a illustration of the formula where E comes from. As we plug in larger and larger and larger and larger numbers, you'll notice that when we put 1,000,000 in here, this gives me close, rounded off, to what E is. We would apply this to an experiment for fruit flies. And how large is the population of fruit flies after 72 years? And so that would be this formula with the 72 plugged in. So there'd be 173 fruit flies within 72 hours. So the joke on this is you may have a lot of friends after 72 hours if you like flies. You're probably not going to have very many human friends. You're not going to have much fruit either. So this is the end of the slideshow here, and I hope it's been helpful to you. Dang.